Okay, welcome to our COFFIES Seminar. It's my great honor to introduce our seminar speaker today. Dr. Piyush Agrawal is currently a postdoc at Southwest Research Institute, Boulder, Colorado. He is collaborating with Lisa Upton and Derek Lamb on improving solar axis metric flow measurements near the poles. He obtained his PhD from the University of Colorado Boulder with his thesis work about inverting solar spectroscopic data using the optimally localized averages helioseismic inversion method. He has also worked on transport of internetwork magnetic flux elements in the solar photosphere. He holds master degrees in astrophysics from the University of Colorado and in applied physics from the Indian Institute of Technology, Dhambad, India. Let's thanks to our speaker again, and I'll pass it to Piyush.
Thanks, Roger. I'm gonna share my screen. Give me 1 second. Cool. Thank you so much, everyone, for joining, and thanks, Roger, for the introduction. This work was something that I did during my PhD with Mark Ras being my supervisor, and we had Basilio Ruiz-Cobo from IIC Tenerife as our collaborator. So this work is basically, like in the talk right now, it's basically divided into 4 different sections. The first section talks about the inversion itself, like what exactly how exactly you're going about in doing the inversion. Second part talks about the issues that we have in the inversions. Third part actually is talking about the OLA being applied to spectroscopic data and inverting for the photospheric thermodynamic parameters of the solar photosphere. Then I'm going to be talking about what can we do to improve our inversion capability of our system. And then the fourth part talks about this tool, the optimal spectral line selection tool, like how we go, like this is like a quantitative metric that we developed to kind of like identify a best set of like spectral lines given. So if you have like 10 spectral lines, how would you actually go about identifying 3 of those spectral lines that have the best inversion capability? In this talk, I would like really I want this to be a conversation style. So if you have any questions in the middle, if something's not making any sense, just like interrupt me and I'll really be happy to answer those questions. To start, I just want to show the amazing image from Aditya's first slide image. Here we're like looking at the photosphere. We're looking at this like the image taken at about, I think, 789 nanometers. So you can really very well see the convection patterns, the brighter plasma coming from the bottom and the darker intercontinental lanes. So if you warp this is just my naive way or naive attempt to kind of like show that, okay, that is a 2D image, but the solar atmosphere that we are after is actually a 3D structure. So in inversions, what we're actually after is this 3D structuring of the atmosphere. Like in the PhD work, we focused on inverting the temperature, the electronic pressure, and line of sight velocity. In this work right now, we're going to be mostly focusing, to keep things simple, we'll mostly be focusing on inverting for temperature. And here, the 2 vertical lines, kind of like I'm just like have been strategically put in a hot and a cold pixel. And for those hot and cool pixels, I'm just like plotting temperature as a function of depth. Just be reminded that this temperature stratification we don't have. That is what we want. I just like pull these hot, and the hot being the blue one, the cold being the green one from a Miriam simulation. So in inversions, when we are doing inversions, we are after this atmospheric parameter, temperature as a function of depth, this being the deeper region, this being the shallow region. Also, in this work, we're going to be focused in the photosphere, where we assume that local thermodynamic equilibrium, the approximation is actually valid. Okay, so this is what we want, the temperature as a function of depth in this talk. But what we have is basically the spectra from each of these pixels. So each pixel have their own set of spectra. A hotter pixel, the more temperature, has like a hotter, like more intensity in the continuum, which is depicted by this blue curve. So here I'm plotting intensity as a function of wavelength. blue being corresponding to the hotter pixel, the green one, which corresponds to a cooler pixel, has lower intensity. This red is just a mean minimum state, and the red dash curve, the red dash one is basically the spectra computed for that. Okay, so if we go from the model, from the atmosphere to the spectra, that is what we call as a forward problem. But when we go from the spectra to infer for the model, that is the inverse problem. That is what we are actually after here. So for each of these pixels, we have the spectra, and the goal is basically to compute or infer the physical properties as a function of depth. All right. So just to kind of like set the problem up like more specifically, here in the left, I have the model, the temperature as a function of depth, and the right side, I have the spectra, intensity as a function of wavelength, basically. So in inversion, in the way we do inversions, like we start with this red dash curve that we call as the guess model. This gray dash curve is what we want, or what we want to actually recover. And in actual and real cases, for this gray dash curve, we only have this spectra, this gray dash curve on the right side. The difference between these two is this red solid curve, which is the delta T, the perturbation. So in inversion, and correspondingly, the red solid curve on the right side is basically the spectral difference between the guess model spectra and the underlying spectra or the observed spectra that we have. So to put it like more setting up the problem, the goal that we are after is like we want to solve for this perturbation, this delta T, that accounts for this spectral difference, delta I. That is what we are after. In this talk, I'm going to synonymously using the underlying model, the real model, the actual model is the same thing, the model that we are actually after, for which we have the observed spectra. Okay, and these are all artificial cases. And we use in our work, we use the SIR, the Stokes inversion based on response function. That method has forward solver. So if we are given a model, we can actually compute the spectra for it. So given this is all the artificial case, we can actually compute all these. All these are like computed actually artificially using the SIR forward solver. So given that what we are after is delta T, and for which that accounts for the delta I, we want something that relates the spectral difference to the model difference. And that is where the response function comes into play. In helioseismology, this would be the sensitivity kernels. So here I'm plotting response function as a function of depth, and each line corresponds to a response function at each of these wavelengths. All right, so in the inset, I have the guess model, and I have the guess model spectra computed here. For this guess model, we can also compute a response function. What response functions are saying that if I make a small change in this model, in this guess model at a given depth, how much my intensity at a given wavelength changes. That is what all is saying. So if my intensity changes by a lot, that just means that my spectra at that depth is very sensitive, versus if it doesn't change enough, then it's not the case.
If I may interrupt with a question.
Yes.
Are these response functions numerical, or are they analytic?
I think SIR computes this analytically, but then there are other methods that are also computed numerically.
Thanks.
Yeah. So this is just response function at a given wavelength for a given depth. We can, this is like, so each of these wavelengths have their own response functions also. So the response function corresponding to a line core has like depicted by this green solid line. It corresponds to this one. So the response function for this wavelength is more sensitive to the shallow region, which is like higher up in the atmosphere, versus if you look at the response function for a continuum wavelength, it corresponds to this blue curve. So which means that the continuum wavelengths are more sensitive in the deeper regions. This differential sensitivity, like different wavelengths are differently sensitive to different regions in the atmosphere, it's what allows you to do or infer for a depth-dependent inversion in the atmosphere. Okay, so this was a differential form of the response function. From there, you can actually write that as an integral, or like more like as an inner product of two vectors, saying that the net change in the emergent intensity at a given wavelength corresponds to my model differences at each depth weighted by their response functions. So this is for one wavelength, and for moving from that, you can actually write that you can stack the equations for different wavelengths. So this is for all wavelengths in consideration, and then you have the response function is like for all as a matrix containing sensitivities for all day depths and or wavelengths that you have. All right, so we again going back, we were actually wanted to like solve for this delta t over t, or fraction. We just use a fractional term here, fractional perturbation as a function of depth. So this being the definition, when we move it to actually applying to, so here you're making a small change in the temperature and seeing how much the intensity changes. When we move it to the real case, the actual case, the delta t does not have to be small. It can be pretty large. That results into, it introduces an imperfection or an error term that we call as the epsilon. The epsilon contains the higher order term in the system that we have neglected when we computed, when we wrote this equation down, but there can be imperfections due to spectral noise and stuff like that. In our work, we didn't like have any spectral noise. We kind of like took stuff to be more ideal. So the only other term that we have is the error from the higher order terms, which itself depend on the perturbation that we are actually solving for. So this first order linear system equation is the most important equation that you have to know or really understand to do inversions. And mostly everything basically comes down to this, like depth inference comes down to solving this linear system of equations. So at the end, we are basically solving or essentially solving AX equals B, a linear system of equations when we're doing inversions here. Okay, so in this slide, it will become exactly clear like how exactly we go about doing inversions. So here we have the guess model that we start with, temperature as a function of depth. For this guess, we compute this spectra, this red dashed curve here, using the server forward solver. And then we have the underlying spectra, so that we also have the spectra delta I, the spectral difference as a function of wavelength. For this guess model, and for each of these wavelengths, we also compute the response function or the response function matrix. Together, when we go back into the first order linear system equations, we have these two terms in the system. This is what we want to solve for, and that's it. So you're solving AX equals B, where X equal is basically the perturbation that you have here. Cool. Okay. So what exactly makes, when you're solving this first order linear system equations, what exactly is that makes the inversions hard? Like in a simple, like if we things were like all fine and cool, like what you would want to go is like you just like take this matrix, compute the inverse of this, and multiply on both sides, and this is the solution that you get, and this being the interpretation. Given the matrix that we have, the inverse of that matrix does not exist, like definitely not in a strict sense. We actually use the SVD decomposition to compute its pseudo inverse. So it just the SVD just means that you're going to write a matrix and as a product of three different matrices, where U and V are your orthogonal matrices, and S has the singular values, and the inverse basically is given by this. In the bottom plot, I'm just showing the singular values of the response function matrix as a function of index. Okay, so the issue when we're computing the inverse of the response function is that the matrix or the system belongs to a severely ill-posed category. What that actually, in a mathematical sense, what that just means that your singular values are decaying exponentially. What this means in a practical sense is that it's very easy for you to amplify any error, any non-zero error that you have in the system. So like to explain that, the inverse has this diagonal matrix inverse, which has terms 1 over SI, which is like 1 over the singular values here. So you're basically like, if you keep the 10 to the -7 singular values in the system, you're basically amplifying error by about like 10 million, by a factor of 10 million. So this ill-posed just means that you can very easily amplify any error, any non-zero error that you have in the system. Further, any error amplified system, any epsilon error amplified system then leads to an oscillatory solution. Okay, just to explain, so the red solid curve is what is the perturbation that we are after. And if we keep 10 of the most dominant singular values when you compute the pseudo inverse of this matrix, the solution is given by this green solid curve. Don't worry about why it's all jaggedy for now. It's just the important part is that the epsilon error dominant solutions are oscillatory in nature. To add to this complexity, the problem is like, even if you compute an epsilon error dominant solution, it's very hard for you to determine that action has happened. This is because your radiative transfer is an averaging process, and a lot of different types or different atmospheric stratifications can lead to the same spectral fit. Again, like it's the spectral fit with is like how much you have minimized the delta I is what leads to you to kind of like say that, okay, my model is corresponding to the underlying model not, but that thing is flawed. So different models that you have, different solutions that you have solved for can lead to or minimize the same, minimize the spectral fit in the same way. Okay, so to get around this this issue that to not amplify the epsilon error, what we do is something we call this regularization. Regularization in a really strict sense almost always comes down to removing the contribution of these small singular values, just so that your inverse does not blow up. So the inverse, which has contributions from 1 over SI, if you remove those super small ones, they have smaller amplitude, and then eventually they don't tend to amplify the error that you have here. It's true for like, even if you kind of like use a node-based inversion, which is like, which is how it's in the spectral polarimetric inversions, to compute a non-oscillatory solution, what you do is like, instead of solving for each of these depths that you have in the system, you only solve for like, say, 5 depths, so that you can actually compute a smooth solution. But indirectly, it's still removing these super small singular values from your system. And that's what regularization means, computing a smooth solution that minimizes the effect of or contribution of this error. Okay, but then the problem is that it seems like like any other thing in science, like no matter what you do, like nothing comes off without a trade-off. So when you do regularization, when you regularize your system by including only a small number of singular values, when you compute the pseudo-inverse matrix, it leads to a regularization error. So it just means that like if we are regularizing more, which means that if you're only using like say a very small number of singular values when you compute the pseudo-inverse matrix, the matrix inverse times matrix is not an identity matrix. It results in like, even though it results in a smooth solution, it also means that the solution that you have computed, because this matrix is not an identity matrix, it can lead to contributions from other depths in the system. Like solution at a given depth will have contributions from other depths in the system. Give me 1 second. Yeah. So, and this is what you have like, so this is like, if you use a smaller rank, this is the green curve is what you get. You can see that you have like overcompensated. So underlying this red value is what you should be computing, but it's a green solid which has overcompensated by this much. This is like a smooth solution of the underlying perturbation. On the other hand, if you do less regularization, which means that you use a lot more singular values, which also means you're using a lot more information in your inverse, it leads to large amplitude term in your in the response function matrix, which in turn amplify this epsilon error, and then lead to this oscillatory solution. So there's this like two extreme regimes in your system. So if you use smaller rank, it leads to more regularization, more regularized smooth solution, but that can have a crosstalk error dominated solutions. If you do less rank, it can lead to epsilon error oscillatory solutions. To summarize and motivate for like why we went ahead and like implementing OLA method in spectroscopic inversions. So inversions require solving an ill-posed system here. If we use a large response function pseudo-inverse matrix, it will lead to epsilon epsilon error dominated solution, which are oscillatory in nature. If we use smaller rank, this matrix inverse times matrix is not an identity. It will lead to crosstalk error dominated solutions. The current methods like SIR, they aim to compute smooth solutions that best fit the spectra. So their intention is actually to compute a smoother solution. While these methods actively minimize this error in your system, but those solutions that you have computed are more likely to be crosstalk error dominated. So, but if your project like wants like if the project that we have like wants a fine scale structuring of the atmosphere, then you would want to actually use an inversion scheme that optimally balances these two errors. And that is what is the intention behind the OLA method. Just to emphasize the bottom line, when we're doing inversions, it's very important that to know our intentions, like what exactly our problem entails. Whether we want a smooth solution, whether we want an ultimately depth resolve solution, we will compute a solution that matches the observed spectra really, really well. So you have to be very careful there. For example, we use Milne-Eddington to do HMI inversion that gives you an average value of the magnetic field. But it's still like a 2D image that you get, but even though the structuring of the B field is like 3D. So again, the intentions are very critical when we're doing inversion. We have to be aware of like what exactly our project entails or what it actually is required. So transitioning to the part two of the talk, the OLA inversion method, which actually aims to compute optimally depth resolved solutions. So OLA stands for optimally localized averaging. The method was invented by geoseismologists and then later was adopted by helioseismologists to infer the internal properties of the sun. We just extended its applicability to spectroscopic data to invert for the depth-dependent perturbation or stratification of the solar photosphere. Okay, so in the inside, I'm just like plotting the first order linear system equations. In the bottom is just if you simply multiply both sides by the inverse of the matrix, what would you get? So this is what in helioseismology would be called as the RLS method, the regularized least square methods. In OLA, you don't actually solve this equation directly. So what the intention in OLA is like you pick a depth, you take a depth, say here like a negative 0.5, and your intention is to linearly combine all of these response functions so that the net response is actually localized at that depth. So it's just called like you're constructing an averaging, or sorry, it should not be sensitive here. It's called you're just constructing an averaging kernel at a given depth. So the goal is you're solving this system, you're solving for the coefficients with which you linearly combine your response functions so that it becomes G, which is user defined. It's called a target function, which is this pink curve here. But given that this is still an ill-posed system, you cannot perfectly solve it. So you only approximately solve it and you get something that's called the averaging kernel, which is this blue curve. It will become clear like how you actually go computing C actually leads to inversions. So, okay, so how do you actually go about doing the OLA inversion at a given depth? Here, I'm just like putting the first order linear system equations, and then instead I have the response function times the coefficients equals your target function. You can only approximately solve this thing. So this is what you call as the averaging kernel. Here I'm plotting what is the length perturbation that we are after. And say we want to do inversion at this depth. So what we do is like we prescribe a target function, which is this pink curve. And then we solve for the coefficient using the response function and also specifying what rank you're using. And then you get this blue curve, which is the averaging kernel. So once you have the C, the coefficients that you have just computed, that gives you the averaging kernel, you multiply both sides of this equation, you take the inner product of this equation with the coefficient. So left side is basically the solution that you get, which is this green curve. And then right side is this interpretation. So coefficient times the response function is basically this averaging kernel. So I'm just going to have replaced that here. So the solution corresponds to the underlying perturbation weighted by this averaging kernel, this blue curve. And just hoping or assuming that this error is not, the solution is not dominated by this error. Okay, once you have this, we can multiply, this is basically the fractional average. We can multiply by the guess temperature at that depth to get the inverted delta T at that depth, which is this green dot here. One thing also OLA gives you upfront is that the width of the kernel that you get corresponds to the vertical relationship. So how you exactly go about doing the inversion is that you take that depth, and one thing that you don't know is like how well you can localize the kernel there. So what you do is like, so even though I'm plotting a kind of like a wide kernel here, you start with say a delta function at that depth. and you solve this system, and you compute the kernel, and you see how much this kernel fits the delta function that you have just put. If it's like fits it really well within the allowed category that you have, you say, okay, I'm going to use the coefficients to compute the solution here. But if it doesn't do that, you kind of like widen your kernel a little bit, and you repeat the process, and you keep repeating it up until you find the narrowest kernel that you can construct at this depth. All right, so this is the inversion, OLA inversion that you get at one depth location at a time. From there on, you kind of like go about, like you repeat. So you constructed the narrowest kernel here, compute the solution, then you move on to the next one, and then you move on to the next one and repeat the process, move on to the next one, repeat the process. So one thing that you have, one thing that's critical to emphasize that in some regions, the resolution, the narrowest kernel that you could construct at each step changes with depth. So your resolution is different. Further, there's a reason why the OLA is only could only be constructed in this region. There's like reason why I have plotted the green dots only in this region. It's because like you don't have a lot of orthogonal or linearly independent sensitivity in this region, and you don't have a lot of orthogonal sensitivity that makes it harder. So OLA has a very set region or depth range over which you can do the inversion, versus in RLS, when you simply multiplying both sides with a response function inverse, you compute an inverse, you compute a solution at all depths there. Okay, cool. So in helioseismology, you assume that when so OLA, given it's applied in helioseismology as well, you assume that your system is linear, which means that this error term is super small. So you don't iterate as such. In spectroscopy, scopic inversions, that is usually not the case. So your perturbations can be super large so that this error term is not small. That just means that you cannot do a really good inversion in a single cycle and single go. So if you use a smaller rank, your solutions are crosstalk error dump. So here I'm plotting the perturbation as a function of depth. Red is in the inline perturbation, the green is the solution, and then the pink curve in the background corresponds to the width of the narrowest kernel that you have constructed. So it kind of like also says what is the resolution of the solution that you have there. So if you use smaller ranks so that you're not amplifying this error, you can only compute a smoother version of the inline perturbation. And you can also only invert at a smaller depth range, versus if you use larger rank, even though it allows you to construct kernels at a larger depth range and also a higher resolution, the inverted solutions are most likely to be epsilon error dominated and are oscillatory. So in a nutshell, what I'm trying to say is like you cannot invert a nonlinear perturbation in a single go using the linear system of equations. So what you do is like you iterate. So you start with smaller rank in the starting cycles, and as your delta t gets smaller as you're updating, which also results in your epsilon getting smaller, you can use larger rank and you refine the solution. So, and if you do that, so that is the iterative OLA that we develop. If you do that, so this is what you get. So plotting delta t on the y-axis, depth on the x-axis. Red is the inline perturbation that you can barely see. It's behind the green curve. The green is the iterative OLA solution that you can get for that. And then pink dots are basically the resolution of the solution that you are getting. I'm also plotting in SIR inversion. What is the existing inversion methods that we have in spectroscopy can do. And you can see that even though it kind of like tries to recover it, okay, here in this region, they are like really off and in the super shallow region where it's very hard to constrain your system. So the point of this slide was like, even though we took the concept from SIR, like how we're iterating and stuff, the results are very different because of the intentions. In OLA, you're trying to solve for an optimally depth localized or depth resolved solution, versus in SIR, you're actually looking for a globally smooth solution. So again, to re-emphasize, one has to be careful, like what exactly do they want when we're doing inversions. And both of these solutions actually still lead to a really good spectral fit. So you have to be careful, like what you're actually after. So the one thing that is, so even though, so if you are actually after a depth resolved solution, you would want to use OLA. versus if you can get away with a globally smooth solution, then SIR is a better choice in our case. So it may actually also seem like you're looking at this plot, it may actually seem like I'm portraying that OLA is this magical thing that with which you can do really good inversions. That is not the case. OLA has its own sets of problems. Even though I'm not discussing any of that, we discussed that in the paper that we recently published. But yes, OLA has its own sets of problems, and but if it comes down to you recovering at higher vertical resolution, then OL is a better candidate versus if you want a smooth solution, then SIR is a better way to go about it. Okay, changing gears a little bit. Now I'm just like talking about like how you can actually go about improving the inversion capability of your system. So here are the equations, the main equations that we talked about, the first order linear system equations and the equation that leads to the averaging kernel construction. I have the spectra and I have the response functions computed for those. So upfront, like one of the ways to kind of like you can improve your inversion capability is like adding more observations that actually provides you with more different response function sensitivity, different types of response function sensitivities. But with our work, we kind of like also realize that when we look at the response functions, we have a lot of these continuum wavelengths in our system for which response function corresponds to these ones. These for the visible, these for the infrared lines, basically. So what we found that like having these redundant sensitivities, like a lot of very similar response functions in your system, actually degrades your overall inversion capability of your system. So if we have a lot of these very similar response functions, which are which peak in the deeper regions, that actually affects the inversion. It's the inversion capability of the system in this shallow region. There's a depth sensitivity bias that is created because of this redundancy. So here I'm plotting all the response function just from the last slide, and here we just like it's a very simple way metric that we developed to kind of like remove these redundant sensitivities. So you can see all the clustering here is gone. So when we do inversions using all of them versus without the redundancy, the inversions are very different. First, like just a step before that. So in the top left here, I'm just like plotting the minimum kernel width that you can achieve as a function of depth, with and without redundancy. So if I made it clear, like the narrower the kernel that you can construct at a given depth, the better, like more resolved solution that you are able to get at that depth. So in red, if we use, so red is the curve or the narrowest kernel that you can construct when you use all the response functions, versus blue is the one that you get when you remove that, when you use only the response function that differ from one another. And we can clearly see that the blue curve has like a slightly wider range, I can say that here, of region where you can do the inversions. And also, but what is more striking is like at each depth almost that you have like, you can construct narrower kernels when you don't have the redundancy in the system. So when you remove that redundancy, what it's doing is like it's removing the depth sensitivity bias, and it's making your system more capable at inverting in the shallow region and also at better resolution at overall all depths, basically. So we kind of like that, okay, it's showing that it's like can do construct better kernels, but can it actually lead to a better inversion or not? So for that, we kind of like started the test case. Here I have a Gaussian perturbation. It's slightly different from the perturbation that I've been talking about so far. The peak location is like, the peak amplitude is like located like in a slightly shallower region compared to the previous cases. So when you're using all the response functions, this is the inversion solution that you get in the red dash curve. But again, sorry, the inversions we're doing is again using the iterative OLA method that we developed. Versus if we use only the non-redundant response function matrix, this blue is the curve that you get, which you can almost perfectly recover the underlying perturbation. Yeah, so this was just like to show, this is just demonstrate that if we artificially manually remove the redundancies from your matrix, it actually helps with its inversion capability. Talking about the fourth section of this talk is this tool that we developed. It's still in a very preliminary work, like, but I think it was, we thought that it was good to kind of like put it out in the community. So Mark, my PhD supervisor, kind of like had this question, always had the question, like when we were starting this project, that how we actually go about identifying what spectral lines to use, like how are we deciding if this is a better set of spectral lines for this case versus another one? To put it like more formally, these are the spectral lines that we use. These are the blends for each of those spectral lines. And the goal here, what we were after is like, out of these 7 spectral lines, how would we go about finding the 3 best spectral line combination that have the most inversion potential, that can lead to the best, that can potentially lead to the best inversion solutions. So for this, kind of like from our work, we kind of like realized that singular value can actually come to rescue, or come to actually can act as the quantitative metric to actually answer that question. So previously, I just like talked the slope of the singular value curve, kind of like it's a measure of like how ill-posed your system is. So that how more ill-posed your system, it's more easy to kind of like, even though it's more easy to amplify the error, the epsilon error that you have in the system. But the slope also indirectly measures like how like different orthogonal information that you have in the system are distributed. So for example, like if this is my matrix and individual columns correspond to my response functions, if all the response functions were exactly the same, then my slope will be like vertical, like my slope will be 90 degrees. Versus if each of these response functions are orthogonal to one another, then the slope is like more going to be flatter. So we kind of like use this idea that like more distinct the sensitivities that we have in the response function, smaller the slope they're gonna be having, which also means that the system is going to be less ill-posed, which also means that their inversion capability is gonna be better. So so with that in mind, just to demonstrate like how, if that actually is the case or not, we kind of like took this perturbation, this red solid curve, and we inverted using this. So formally put out, like for each of this 3-line combination, we removed the redundancy when we did the inversion, and then we also computed their slope. So and this is what we get. So on the y-axis, I'm plotting like how much the inverted model matches the underlying one when we invert using a given set of given 3-line combination. On the x-axis, I'm putting the slope of that singular value curve for that combination. Don't worry too much about the big dots here. Just focus on the green ones. So each green dot corresponds to inversion done using a given line combination. And we can see that the combination that have the smallest slope correspond to are best able to recover the underlying perturbation. There is one glitch here, and we can talk about in detail later. But in overall, this metric is something that works. So so in here, so the blue was like when you used all the inversions, all the lines, the inversion solution when we use all the lines, versus when we use only the 3 best lines identified. It corresponds to the green curve here, where you can like barely see it's like all mixed in, but it's still able to like recover the underlying perturbation really well. And these like highlighted black lines are the ones that we identified from this 7 spectral line set. Moving further from there was, okay, we have identified the spectral lines that have the best inversion potential, but can we actually also go about measuring what that potential even looks like or not? So we kind of like looked at, okay, it seems like, so we kind of like use the kernel width that you can like narrowest kernel width, that kernel that you can actually construct as a function of depth. So for the identified lines, the kernel width versus as a function of depth, and depth range of which you can do the inversion actually gives you that inversion capability. It does, it's an estimate. All of this depends on the guess model because the response functions are also computed for the guess model, but it still gives you an estimate of like what that inversion capability looks like. In here, the 2 curves correspond to the rank extremes that we have, the least amount of information, the minimum width kernel that you can construct with the least amount of information, and with the most amount of information that you have, that you keep. And yeah, so this kernel width that you have, the minimum width kernel that you can construct as a function of depth can actually give you an estimate in the inversion capability. With that, I'll take questions. Oh, wait, sorry. This is just the summary slide. This is the first order linear system equation, the most important equation that we have, that we solve to do the inversions. There are two different error types: the error epsilon, which depends on the higher order terms, and the crosstalk error, because of the smoothing, because of regularization. Existing spectral polarimetric inversion methods specifically focus on minimizing this error and compute smooth solutions, but their solutions are likely crosstalk error dominated. The iterative overlay method that we have developed computes optimally depth resolved solutions, and those the method is like more so suited to recover the fine structure of the solar photosphere. I talked about the redundancies and response functions and how they affect the inversion capabilities, and artificially removing those redundancies can actually help improve the inversion capability of the system. And even though we demonstrated that using the iterative overlay method, but we believe that it should be true for all methods out there. So if the scheme is employed, yeah. And in the third part, we talked about the tool, the quantitative metric to identify optimal spectral line combinations. We kind of like showed that the slope of the singular value can actually help and act as that metric, even though this is a preliminary work, but it should be true when we extend it to a multivariable system. Once we have identified the optimal spectral lines, the kernel width as a function of depth can actually give an insight into what that inversion capability actually looks like. Yeah, and so these two pieces that we talked about, this is not specific to the overlay method. These can be implemented to any inversion method out there. So yeah, with that, I'll take questions.
I see someone raised hand. Sabani?
Okay, thanks, Piyush. That was very interesting. And since I do helioseismic inversions, I couldn't help in my head trying to find analogies and differences. So if I can start with your RLS type inversion, I noticed that all you were doing for smoothing is just restrict the number of singular values that you use.
Yes.
Now, in helioseismic inversions, we know that doesn't work very well either.
Yeah.
And instead, we use almost all the data and then explicitly smooth the solution,
Okay.
using usually a second derivative smoothing, usually.
Okay.
Has that ever been tried out in this field? I'm curious.
I'm not entirely sure. Like all the ones that I have read about, they're mostly node-based or Milne-Eddington, which just like gives you an average value. It's like there's nothing depth in ME as such. I am not sure that even so. I think because you even like if you look at the response functions here, you just don't even have the information there. There's like I think in heliosysmology you have like a lot of these oscillating sensitivity kernels that can like maybe help you, but in response functions here they're like all on the same side. It's very hard to like construct anything. So I think because the solutions are very, very unstable, like here I'm just like talking about like out of the 120 in my case, or like over 100 non-zero singular values that you can actually technically keep, this 12 of them can like correspond to 99.9% of information.
Okay.
So you don't even have any kind of information. So things are much more unstable in spectroscopic case. So I don't think people have even tried that because it's very hard. Like if your error, the epsilon error is like large, it's very, very unstable.
Yeah, that makes sense. So my second question is about the OLA part. You mentioned that you had to iterate because you were not really in the linear regime.
Yeah.
How successful are you in getting to the same solution if you start from widely different guess values?
So, I mean, like in my case, I think our guess was already super. So it's kind of hard to say if it's like, it's definitely far off. Like, so in my case, I started with like, say, this flat one and like starting to recover the red solid one that's behind it. So I think I have not tried like even going even further when I'm iterating. I just like said, okay, my perturbation was like 600 Kelvin, which is actually not a small perturbation to put to recover as such.
No, so what I mean is you started with a guess model at 0.
Yes.
To essentially get something at 600 at one of the tau values.
Yes.
Suppose you start with a guess value of, say, 700. Will you get back to zeros at the correct places and the proper peak at the proper place?
I think it will. I think so what we realized with iteration, it was not more so of like having, I'm like, obviously if you go super far off, it's gonna be really, really hard to like do anything. So if you're reasonably far off, so the problem that we faced with iterative OLA was like, there's a set window outside of which we are not updating or recovering. So if we keep updating this region, say this red one is my perturbation. I should have had that slide. I should have that. And it goes to 0 in outside of this region, like outside like -2 or something. So if I have a non-zero perturbation outside of my window, and if I keep iterating, what happens is like I keep bringing the information from outside of the window to the inside as I'm iterating. And that is a bigger problem with OLA.
Okay, I see.
Yeah, so that's what we are still working on. So we are like looking at that hybrid approach of like using SIR to kind of like give us like a mean state or like mean stratification so that we don't have a lot of like this outside of the window perturbation, and then we do the fine scale inversion on the inside using the OLA. So, but still that is still in work. So talking about like in that, if you have pretty big perturbation or relatively big perturbation within this region, it should not be a problem, versus if you have non-zero perturbation outside of the window, that is more big of a problem in OLA.
Okay.
Yeah.
Thank you.
Thank you.
Jason also raised hand.
Yeah, thanks. Yeah, thanks, Piyush. Like Sarbani, I was making those comparisons as well. So you've shown some pretty idealized cases, and in this case, you're able to use the width of the averaging kernel as your metric for how good you're doing. But in reality, when there is noise, then you have things like L curves and noise amplification that you have to worry about. So I'm just curious, do you have any results from real spectra that have real noise in them, and then you do have to make sort of, like you said, intentional decisions that here you really didn't have to?
Yeah, I mean, like I did that in my PhD. I'm like, so I should have all those plots here. I just don't have it here. So in the PhD work, we did put some random noise in the system and try to invert using that. I think what we realized was that just putting random noise just sets the sets the lower limit of like how well you can actually do the inversion, because once you get to that delta I, you're only fitting the noise. So that results in, okay, this is best that we can do if we have. So the more the noise is, like, you have to stop at a certain level, and beyond that, if you keep iterating, you're gonna be like fitting the noise at that point. So I kind of like feel that just having the noise just like sets that boundary. So we were like, okay, we already have issues. So to answer your question, so in this slide, I don't have that. I have that in my thesis. But we kind of like moved away, kind of like because we had other problems to deal with in the OLA, like this outside of the OLA window, bringing information into the window, and we were like working on that. So once we have carefully taken back, carefully worked on that piece, we're gonna go back and look at the noise and like look at more in detail. Yeah.
Okay.
Yeah, the L curve is also very unstable here. Like I see what you're saying, but like you have literally like within like 10 rank or something, all of them, like literally sitting at that corner in that L curve. So it's very hard to like think of this here. You're moving from 5 to 10 and your solution becomes this. And this is what is actually leads to the best spectral fit solution. So you don't even have enough information to constrain, like it's very hard to constrain stuff here. So that L curve, the point is like sitting on top of like 10 points in there, basically. So, and yeah, if you have noise, you're gonna even add more point to that location. So making it like even harder to do inversions.
Right. And you mentioned, I think that if you do the forward problem from here, the spectra are almost all identical. I mean, because that's another way to discriminate
So
between inversions.
I think like the spectral fit, like I think I'm just talking in terms of the Elvin norm of the total difference, delta I vector. The spectral Elvin norm of that is just like for the OLA, it's like because that's on top of another, is close to like 0.01. And for comparison, the SIR is like say 1 or 0.9 or 0.5 or something like that. So it's still super small. I'm not giving you any visual here, but like they would be acceptable. That's what I'm saying. The spectral fit would be acceptable for both of these solutions.
Okay, thanks.
Okay, there's one more hand raised in from Andre. Andre, are you there?
Andre is loud?
Yeah, we
Now-
can hear you. Yeah, we can hear you.
Okay. I am from Kislovodsk solar station. We use some different kind telescopes. One is magnetograph from photospheric line, and we have 2 seconds telescopes for Iterative light and a Crichton line. We have some problem. One problem is for magnetograph, we need to measure some magnetic field, and we use some spectrographic data, and we need some fit between line.
I can barely hear you.
Sorry.
I can barely hear you. Sorry.
Okay. We use a little different data, a little different some fit. We use some GUO method. GUO, it's a very fast method fit some expansion function to line, to spectral line. What do you think? It's working or not? Looks like for us it's working. What is difference between OLA method and GUO method?
What is the difference between OLA and what?
GUO method, it's some fast fit to Gauss function to curve.
So I'm not getting like what your other method that you're talking about is here though. Sorry.
Okay. We have a lot of some image of spectra, and we need to found with some central Gaussian right? And for this we use GUO method. It's published in 2019, I think.
Hey, can you maybe type it? Type the method's name or like a
GUO.
GUA. Okay.
We
Okay,
can also
GUO
talk
method.
offline if that
It's
is.
a fast method for feed Gaussian to line. Not to line. It's method to feed to Gaussian to some curve. And we use this method for found some magnetographic data or atmospheric light. What is how your method? What is difference? Online method and GUO.
Yeah, I don't think I'm
Okay.
kind of like aware of the other method as such, so it's gonna be hard. It will be hard for me to kind of like compare what exactly is the difference between these two. I'm sorry.
But your curve is Gaussian or not?
My what?
It's like Gaussian.
What is Gaussian?
Option. Maybe.
My
How?
option.
It's
I think
Gaussian.
he's asking if your method is Gaussian.
What is the method?
How you hit the spectral line? It's a Gaussian line or what?
Oh, yeah, I don't have any, at least in the test cases that I have, I'm not putting any, the line of velocities are 0, so they are Gaussian. Yeah. I have not checked it, but they should be. I'm not fitting a Gaussian to the spectral line directly. So, yeah.
Okay, I think if we have follow up on this question, maybe you can like do it through email.
Yeah.
To make it more clear. Yeah.
Yeah, this is my email. You can just like shoot me an email. I think like that would be better. We can just talk one-on-one and it would be, we can talk more about that. Just shoot me an email, please.
Okay, thank you. We are like right at 1 hour time now. Thanks again to our speaker, especially thank you for like the discussion afterwards. And as before, the seminar will be put online. The recording will be put online. So thanks to Piyush again, and see you next month.
Thanks, Riju. Thank you so much.
Thank you.
Thank you. Yep. Bye.